In 5.5, we are going to look at how we can solve trigonometric equations. Of course, when we have an equation, we have a trigonometric function set equal to some outcome. And so it's our goal to find out what are the angles that give us those particular outcomes. So what is a trigonometric equation? Well, a trigonometric equation is just an equation that contains trigonometric functions. Very simple one, we could say sine of x is equal to some value, like negative root 2 over 2. This is a statement of equality, and every time we have a statement of equality, we have an equation, right? So there's an equal sign involved in it. And so there are generally solutions we want to try to find out if indeed there are specific outcomes like we have here, negative root 2 over 2. Equations that are true for all values in the domain of the variable are called identities. We looked at those in Chapter 5. For example, we saw that sine of x is equal to the cosine of pi over 2 minus x. So here we have a statement involving an equal sign that is true for every value of x, all the values in the domain. Domain are the values that we're allowed to plug in to a given equation or function. But when we have just a statement here of equality, this is called a identity, and it's true for every x. So there isn't necessarily anything to solve for like we would in the above statement. When we solve a trigonometric equation, it means to find its solution set. That means we need to find what are the solutions for all the values here. And we're going to look at an example of that, but just to give you a bit of a example, just to specifically show what I mean here. Actually, let's do root 2 over 2, the same one I have above, negative root 2 over 2. Remember that the solution for this, we know, is 45 degrees or pi over 4. We're going to genuinely keep this in radians and practice that. But we know that sine is negative in sine, which is y, right, is positive here and here and negative here and here. So if I have a negative root 2 over 2, that means we have a 45 degree angle here and a 45 degree angle here, going all the way around, There are actually two solutions for x if we're only looking in the domain 0 to pi over 2. So if we're looking in the domain of 0 to pi over 2, we would have pi plus one more pi over 4. So 5 pi over 4, right? 4 pi over 4 would be pi. And then we went one more 45 degree past that. And then here we, in the fourth quadrant, if we went all the way, we would have 8 pi over 4. So I know this would be one less than that because its reference angle also is pi over 4. So we're taking one away from 8 pi over 4, giving us 7 pi over 4. Now, this is just for the domain, x being from 0 to pi over 2, or 2 pi, we should say. If we wanted to show all of the solutions, sometimes we limit it and say only show the solutions within the first rotation, right? 0 to pi or to 2 pi. But sometimes we might want to express all the solutions. And so we have some formulas that we can use to help us do that because this is all circular. Remember that these values occur over and over and over again. In fact, there's an infinite number of angles that would give us negative root 2 over 2. And so we have to kind of express all the solutions in a bit of a formula style. Here's a table that we can use that, of course, gives us the patterns that we see here. So I want to help kind of break this down a little bit for us. So with sine, which is y, all right, sine is on the y-axis. It's the y value on the unit circle. With sine of x equals some value for some angle. I know this is a bit of an awkward statement, but we're going to use x and we're going to use theta here. X has to represent the solutions, right? So these are both angles, but we just want to differentiate between what is the solution we find. So for example, when we had, sine of x equaling negative pi over 2, we found the first one. We can say whatever that angle was, and in that case it was 5 pi over 4 plus 2 pi n. 2 pi, remember, is a full rotation. So my solution, let me draw a little picture here. My solution was in the third quadrant, right? That was the 5 pi over 4. And with that, we know that every time we come to this, we're going to have a solution. 2 pi is one rotation. N represents an integer. And we generally use n for whole number, integer type of numbers. So like 1, 2, -1, -2. A value of 1 for n would be one rotation around, right? So we'd be going here and then around again, coming back here. And so that is telling us every time we hit this part here, by adding that to n pi, so n is kind of our variable in our answer, that we're hitting that one angle. But adding 2 pi to that would give us, 13 pi over 4 instead of 5 pi over 4. But also we had the other angle. If we took pi and we subtract alpha, that would put us for this angle into this quadrant, and we add 2 pi n to that as well. So if we follow this formula, if we go our angle answer plus 2 pi or 2n pi, we generally put pi last if pi is a part of an answer. So it's a little awkward, I know, to have that there. But 2 pi n, 2n pi, it's hard for me to say. I want to say 2 pi n. And there's nothing wrong with writing it that way, but they chose to write it this way. And then we take pi and subtract that value. So if I took pi and went minus 5 pi over 4, that would also take me back to this spot. And of course, if we add 2 pi n to that, that would take us around and back to the same spot. For cosine, it's a little bit different because cosine is x. For cosine, which is positive in the first, because cosine, remember, is x, it's positive in the first and fourth, and then negative in the second and the third. Also with negative pi over 2, let's just go with pi over 2. Let's say we have cosine. I just want to use an example of something. So root 2 over 2, we know that's 45 degrees, right? So that's positive, so that's positive 45, or pi over 4. So that's one of my solutions for x, pi over 4. Then we would write that as pi over 4 plus 2 pi n, or 2n pi. I probably naturally would write it this way, regardless. The other one is in the fourth quadrant. So if we keep going around and end up here again, that same value there, for 8 pi over 4, or 2 pi minus 1 pi over 4 is 7 pi over 4. We would let me actually get that with the formula they have there. So let me write that out. So for the second one, x is also going to be equal to 2 pi minus pi over 4. 2 pi minus pi over 4. Well, this is 8 pi over 4, right, is how we could rewrite that, so we can do these. That gives me the 7 pi over 4. So I just wanted to show you how I got to that. So you can see how this formula takes us there. And then I want to put plus 2 pi n. This would show me all the solutions for this particular equation. So we can use this little table here to help remind us, but really this is just, I got that without using the table, just using the logic of where is it positive, where is it negative. And that's the kind of thing that will stick with you from problem to problem. For tangent, tangent starts repeating after pi, and so we just have to go the one thing, the one angle, plus n times pi. We don't have to worry about the second one, because for every pi, for example, with tangent, it's positive here, and it's negative here and here. So if I have a solution that's taking me into this quadrant, all the solutions, if I add pi to it, would take me again up to here, also where it's positive. When we go pi again, it's going to take me right back here. So it simplifies it for us because we don't have those positives in these odd quadrants like we have with cosine and sine. All right, so actually let's work through a few of these. Find all the solutions of each equation. So notice they're saying all solutions. That means the infinite set of solutions. We can't list them all in a table or a set. And so we need to write out that 2 pi and that pi when it comes to tangent equation. Express all solutions in radians. So we're going to do these for radians. So first of all, let's just find the most basic of these. So for sine of x equal to root 2 over 2, kind of did one of these, but with a negative. Sine of x, remember it's always sine of something. This is our angle. We know one of those is pi over 4. So that's where I'm just going to stick with for now, and then we're going to build on that for each one of these. For b, and actually, sorry, we need to list both of them. Pi over 4, and sine is also positive in the fourth quadrant. And so we also had this, second quadrant. I'm going back in my mind to cosine. Sine is positive in the first and second. So we have the first quadrant, pi over 4, and then we have the second quadrant, which is pi over 4 from here. So if we think of this as 4 pi over 4, that's pi, and we subtract pi over 4, that gives me 3 pi over 4. So we have our two solutions there. And then for b, cosine negative root 3 over 2. Cosine x equals negative root 3 over 2. All right, we know we get root 3 over 2 at 30 degrees for cosine. Cosine is x. Thinking of that, remember, if we're just going up barely, that unit value is really close to 1. So it's the root 3 over 2 when it's pi. So when we solve equations, remember our goal is always to get the x by itself. And so the way that we do this with sine, cosine, and all these, I just want to take you through that. All right, we always use steps. Steps are important. We can remember how to do it. The goal is to get x by itself. And so we use something that we introduced earlier called the arc sine, which is the inverse function. If I take the arc sine, so the sine minus 1, of sine of x, and I do that to both sides. I'm taking the arc sine of both sides. This just becomes x. I'm basically undoing the sine. I took the sine, now I took the arc sine. I'm left with the x value. So this is the way we kind of undo the sining of an angle. We take the arc sine. Now remember that for sine, we limited the range, the outcome here. And we limited the range for arc sine so that all the positives would be in the first quadrant and the negatives would be in the fourth quadrant. This is a positive root 2 over 2. And so because we're using the arc sine, we would say the solution here is pi over 4. And that is how we're solving this for x, right? Literally just like going through the steps and solving the equation. For cosine of x, we're doing the same thing. I'll move this over a little bit. I don't like putting the arc sine on the back, but I didn't leave myself enough room. So I'm just going to go ahead and move that over a little bit. To solve this then, we want to get x by itself. I'm going to take the arc cosine of both sides. If we do it to one side of an equation, we have to do it to the other. The arc cosine of x is x. And then the arc sine, we're doing a negative cosine. Cosine positive was in the first and negative was in the second. And so we know the arc cosine of negative root 3 over 2 is the 30-degree reference angle in the second quadrant. And let me just help you picture that. So we're going all the way over here where we get a reference angle of 30 degrees. So that's pi, well, since we're dealing with 30 degrees, that's pi over 6. So I go 6 pi over 6 minus 1 pi over 6. That is 5 pi over 6. So the arc cosine there is 5 pi over 6. And for the last one, C, just so you saw me doing that there, taking the arc tangent on both sides and so on and so forth, we can actually just kind of skip that part. You don't have to physically do that, but put it over here. Oops, put cosine, that was in my head. So x is equal to the arc tangent of negative root 3. Now I want to touch on something here with tangent, because there's the two solutions we get at 30 and 60. One of them is the square root of 3, and the other one is the square root of 3 over 3. Right? This being the smaller of the two, smaller outcome, because we're taking the root of 3 and we're dividing it by 3. So obviously that would be smaller in terms of its outcome. And this would be the larger one. Now, stick with me here. Remember, it happens at 30 degrees and it happens at 60 degrees. So I'm giving you something here to that you can logically remember, so you don't have to always reference the chart. So here we have 30 degrees. Here we'll draw 60 degrees. Those are the two and one of them gives us root 3, and one of them gives us root 3 over 3. Remember what tangent is. Tangent is the TOA part, so it's opposite over adjacent, right? So this side divided by this side. You can see at 30 degrees, the smaller side is the opposite, and the larger side is the adjacent. And so if I take a small and divide it by a large, like 1 divided by 2, for example, gives us 0.5, I get a smaller outcome. And so the smaller one, which is this one, we know is tied with the tangent of pi over 6, which is 30 degrees. We get the smaller outcome. Isn't this ingenious? And then with the 60-degree angle, we have a larger divided by a smaller. So just like 1 over 2, if we flip that, 2 over 1 gives us 2. That's a larger outcome. So I know that this goes to the pi over 3. If you haven't already memorized that, I just gave you a way to kind of pull it up when you need it without always having to reference your sheets. All right, so this is the larger, obviously, but it's negative. But that means, and tangent is positive in the first and negative in the second. That's how we limited its domain. It's also negative in the fourth quadrant, and actually, for tangent, we limited it like sine to the arctan. We limited the range to the first and the fourth. And so here we would want to use the fourth quadrant angle. Root 3 over 3 is the larger, so it gives us pi over 3, but it's negative pi over 3. In the case of arctangent, sine and tangent are limited to the first and the fourth, and we actually use the negative there. We don't do the positive, which, the positive co-angle of negative pi over 3 is 6 pi over 3 minus pi over 3, so 5 pi over 3. So those are my initial solutions. And again, we're doing this because we're using the arctan. Oops, didn't mean to erase that. Using the arctan and the arc cosine and the arc sine to solve the equation. So now let's take it. We found kind of the initial solution for arctan and all that, arc sine and arc cosine. So let's use that formula we had in the table there to come up with all the solutions. So the solutions for sine of pi over 4 giving us root 2 over 2, we already have one of them. We have pi over 4. So I have pi over 4, and we're going to put plus the 2 pi n, or 2n pi. I don't really care which way you write them. Now, for the next one, the other solution, we want to take pi and subtract that solution we found, pi over 4. So we plug this in to that formula there, pi minus pi over 4. So think of this as 4 pi over 4. That's going to put us in the second quadrant where our outcome is also positive. And then we're going to say plus 2 pi n. So that's 3 pi over 4 plus 2 pi n. The formula there, with pi minus alpha or whatever your solution angle is there, is meant to give you the two places where it's either positive or negative, right? There's two places where we get a positive outcome, root 2 over 2, and two places where we get the negative root 2 over 2. And when we add the 2 pi n to it, we're basically showing all the solutions, the infinite solutions that there are. Now, if we were just listing the solutions in an interval from 0 to including 0 all the way up to 2 pi, not including 2 pi because that would just give us a replication of 0, right? 0 and 2 pi are on the same spot. We go to 2 pi, we're here again as well. So we include 0, we don't include 2 pi. This gives me pi over 4, where n is equal to 0, so we're kind of ignoring that, and the 3 pi over 4. That's kind of a technical term, sorry, that meant to be a comma, not a plus. Basically, we're just listing the two actual solutions we found and that we added 2 pi into. These are the two places where the sine of x gives us positive root 2 over 2. So again, look, for cosine then, we had our solutions for negative root 3 over 2 for x. Notice how they wrote this kind of like they have it in the table. They said, remember how it was kind of awkward? It was like cosine x equals cosine alpha. So this is just the alpha part of it. And so it's kind of, they're writing that out that way so that you can see how that formula works on the table. 5 pi over 6 was our solution. So x is equal to 5 pi over 6 plus 2 pi r for wanting to 2 pi n, if we're wanting to list all the solutions. But then x also has a second angle in the third quadrant. Remember, cosine's negative here and here. So you can use these formulas, but for me, I like to draw the picture and see what it is. But the formula will take us to the solution as well. And for cosine, we're going to take 2 pi minus 5 pi over 6, our alpha here. And the thing, it says 2 pi minus alpha. Okay? Our alpha is 5 pi over 6. So if I take 2 pi and I subtract 5 pi over 6, right? 5 pi over 6 took me here. If I subtract 5 pi over 6, that's kind of taking me back there, but what it ends up giving me is the value here. If I take 2 pi and I subtract this out, I'm basically left with this. 2 pi is like 8 pi over 4, or I'm sorry, we have 6 there, so 12 pi over 6. 12 pi over 6 minus 5 pi over 6 gives us 7 pi over 6. So the outcome here is 7 pi over 6, and then we're going to add plus 2 pi n. See how we could just come up with that without necessarily having to use the formula. I like to do it this way because for me it makes more sense. I don't have to try to memorize a formula. But, 6 pi over 6 is pi, and we know we want to add a pi over 6 to that. And so if we add 1 pi over 6 to that, we get 7 pi over 6. To me, that's a little easier way to do it than to have to reference a formula, because I know where they're positive and I know where they're negative. So, and to that, we just add 2 pi n. That takes every rotation into account. So the solution set that we found for the interval here, 0 to 2 pi, is 5 pi over 6 and 7 pi over 6. If we're just limiting it to the domain 0, including 0 to 2 pi. And for tangent, if you remember tangent is positive. Actually, we have a negative, sorry. So tangent is negative in the third and the fourth quadrant. But for our solution here, which was limited to the first and the fourth, our solution was this pi over 3, negative pi over 3. That took us into the fourth quadrant because the range was limited by the arctan function, the inverse function for tangent. So we can list that as one of our solutions. If we're listing all the solutions, we'll say negative pi over 3 plus pi times n. Remember, tangent only repeats every pi. So negative pi over 3 plus pi of n would be all of my solutions for this trigonometric function. And that is my solution for x. We'll put x there equals. So we're always trying to solve for x, or whatever variable it is that they give us. Now, if we want to give the answers that are in the interval 0 to 2 pi, notice that in this case, because we took that negative pi over 3, that's not in that interval, right? The interval has the lowest value of 0 all the way to 2 pi, not including 2 pi. So we need to actually use this pi n. I need to add pi. If I want to find the solutions that are in that interval, I need to actually add pi for n equal to 1. And then I need to do it for n equal to 2. So let's just add pi to negative pi over 3. So negative pi over 3 plus pi times 1. I'm going to put this as 3 pi over 3, so we have a common denominator. It gives me 2 pi over 3. And if we add one more pi, that is adding 6 pi, or just adding another pi to this one. So you can either think of it as adding 3 pi over 3 to this, which would give me 5 pi. That's the other one, 5 pi over 3. Or you can think of it as, formula-wise, negative pi over 3 plus pi times 2, or 2 pi, and being 2. Which would give me 6 pi over 3, right? That gives me 2 pi. And 5 plus negative 1 also takes us to 5. 6 pi plus negative 1 is 5 pi over 3. So formula-wise, you can work it, but you can also just add another pi to what you just found, right? We're basically going to here. We got this. This was 2 pi over 3. And then we added another pi to get us to here. That's adding a pi, or adding 180 degrees, right? That takes us over there, and that is 5 pi over 3. One more pi over 3 would take us to 2 pi. So we're just one less than what we need. 6 pi over 3 would be 2 pi. So here are the two solutions that are within the interval 0 to 2 pi. Okay, what about something that's a little more complicated than just sine of x equaling some outcome? If we have some other things going on here, you know that these get shifted and the amplitude gets multiplied by 2. And okay, how do we solve this? Remember, our goal is always to solve for x. That's our goal here. So really, we're just going to use the same techniques that we used when we had, for example, you can think of this as 2x, where x is something's being added to it. Let's say it's plus 1/4. We'll just take the angle part out of it. Plus 1 equals 2. The first thing we always want to do is to get the any additions and to get the term that has the variable by itself first. So we'd subtract 1. We're going to do the same thing here. We're going to subtract 1 from both sides. Then I have 2 sine x minus pi over 4. Just going to rewrite it, equaling 1. And over here, if we did that, we would just get 1 equals 2 times parentheses x plus 1/4. And then we could divide both sides by 2 and get rid of, that's one thing we could do. We could also distribute the 2, but we're not going to do that here because it wouldn't be practical. So I just want to show you, we get the x term that has the x by itself. We've done the divisions. And so I'm going to do the same thing here. If I divide both sides by 2, we get sine of x minus 1/4, or sorry, not 1/4. In this case, pi over 4 equals 1/2, right? And now we need to undo. Now here, this kind of isn't quite the same, because we have the sine here. But to undo the sine, we just do the arc sine. So I'm going to have over here x minus pi over 4, because we're doing the arc sine to both sides. I'm just not rewriting it in here. Here, I'll do that. Arc sine to both sides, right? And so that gives me the arc sine of 1/2. Sine for the positive with arc sine, that's always in the first quadrant. And to get 1/2, that's always for y, to get 1/2, that's our 30-degree angle. Again, just as a reminder here, when we're looking at the unit circle, and we've barely tapped up here, the x is root 3 over 2, but for the y, we're at the halfway point. So for 1/2, that gives us pi over 6, so 30 degrees, as our outcome. So now we have pi over 6 equals x minus pi over 4. Now, because we're going to be doing it for the whole thing, you also want to keep in mind the other angle, which sine is also 1/2 at 5 pi over 6. So I'm going to also just put also 5 pi over 6. 1 less than 6 pi over 6. Okay, so we've got our two solutions. Now, they're plugging it into that formula here, and that is important to keep in mind. If we go pi minus 5 pi over 6, using that formula, this would be 6 pi over 6. That gives us our 5 pi over 6, right? That was the other one we were keeping in mind. So now we have what's over here. Now, these are not my solutions. Those are just the solutions without the x minus 4 there. And ultimately, x minus pi over 4, sorry. Ultimately, what we want to find is the solution just for x, right? So right now I have plus 2 pi n, and I'm going to actually just sort of bump that over to the side for now, plus 2 pi n, because I want to solve this for x. So I need to get rid of this pi over 4. I need to add that to both sides. Right? So we'll add it here, and this gets x by itself. And we're going to put the solution that we get for adding these together once we do that. 6 and 4 have a common denominator of 12, or at least common multiple of 12. So that would be 2 pi over 12 here. And adding 3 pi over 12 here, 3 times 4 gives me 12. And so that, adding these two together, I get 5 pi over 12 plus my 2 pi n. On the other side over here, I've got the 5 pi over 6. So again, I'm going to rewrite this. Equals, and we have 5 pi over 6. And then I'm going to move this over to the side to 2 pi n. And I'm going to do the same thing. I'm going to add pi over 4 to both sides to get the x by itself. Remember that the goal is to get the x by itself. Here I need to multiply the top and the bottom by 2, so that's 10 pi over 12 plus, and here again we're going to do 3 pi over 4. 3 pi over 12, sorry. 3 pi over 12 gives me pi over 4. Adding those together, I get 13 pi over 12 plus, let's bring this down, my 2 pi n. So these are the infinite solutions that I have here. And if we were just looking at the ones that are in between 0 and 2 pi, let's examine that next. So what we saw on the previous page is that for the interval 0 to 2 pi, the two main ones we found there were 5 pi over 12 and 13 pi over 12. Are there more within that interval? So what we need to do is to kind of examine what happens if I add 2 pi to this, right? So, for example, let's start with 5 pi over 12. That's something that is in the, well, I believe 5 pi over 12. We'd have to figure out what it is as degrees, but let's try to add 2 pi to that, right? Because that's one of our solutions. 2 pi would be 12 pi over, we need 24 pi. Sorry, let me start over there. We're adding 2 pi. I'm just going to give us a little more room. So I'm going to try going 5 pi over 12 plus 2 pi. That would be 24 pi over 12. And 24 pi over 12 would give me 31 pi over 12. This is way outside of the 2 pi, 0 to 2 pi, right? Because we're adding 2 pi to it, we actually could just kind of ignore this part, because if I add 2 pi, it's obviously going to be, since this is positive, something outside of the 2 pi range. I'm adding 2 pi to something that's already large enough. And so I don't even need to check the 13 pi over 12. You can kind of change those into degrees if you want to, remembering that pi is equal to 180, and you can easily see whether it's going to go outside of that. So in this case, these are the two solutions that lie within it. So we'll put those into set notation. We'll put those into braces. Braces are what we use to show a solution set. So whenever we have more than one, we'll use that there. And this concludes actually the first part of our solving trigonometric equations. We're going to look at some more in-depth, more complicated ones in the next section. But this one will start us off in developing our skills to solve trigonometric equations.